A positive series, every term is positive. Denote this partial sum as Sn, show that if alpha is bigger than 0, then this infinite sum is convergent. The same infinite sum is divergent if alpha is smaller than or equal to 1, at the same time if Sn approaches infinity. So first, let's look at this graph. Function is 1 over x to the power of alpha, the same alpha. So I'm looking at this graph should be decreasing because alpha is now bigger than 1 over x to the power of alpha, must be decreasing. So I'm looking at this this definite integral, integral from Sn minus 1 all the way up to Sn. Now, if I say this rectangle is smaller than the area of this curve, right? So that must be true. So that means if I replace x with Sn, then do the integral, the rectangle is smaller than this area. So which means integral Sn minus 1 to Sn 1 over x to the power alpha dx. Right, so if I replace x with Sn to the power alpha, right, that is equal to Sn minus 1 over Sn to the alpha. That is essentially An over Sn to the alpha. Like I said, that must be smaller than the actual integral. Smaller than the actual integral. Right? Sn 1 over x to the power alpha dx. So we can sum them up. So let n start from 2, because I don't want to start from 1, because I don't know what S naught is. But it's okay for me to just miss one term, because one term does not impact the convergence. Right? So I'm looking at this partial sum. I'll let k go from 2 up to n. Later we're going to let n approach infinity. Of ak over sk to the power of alpha less than or equal to sum of the integral, right? So integral from, for example, S2 up to S3, S1 up to S2, S2 up to S3. So in the end, we have S1 all the way up to Sn, 1 over x to alpha dx. And so this should be easier to calculate. So that must be x to the x to the minus of 1 minus alpha. And I also have times x to the 1 minus alpha, evaluated from S1 to Sn. Right. So that is essentially equal to, I want to put x at the bottom. I want to put x at the bottom, because then I can use 1 over x to the power of alpha minus 1. Right? 1 over x replaced with Sn. Right now I can have alpha minus 1. Or just flip it. Minus 1 over S1 to the alpha minus 1. So right now, if I'm thinking, if I don't know whether we're not given Sn if it's convergent or not, right? If alpha is bigger than 1, we don't know it. Now, suppose in the worst case scenario, suppose if Sn is divergent, right? Because it's positive series, it has to diverge to positive infinity. So that means we have positive infinity at the bottom, positive infinity to the power of positive power. Right? So that means this part has to converge, right, as n approaches infinity. So using comparison test, right, this positive infinite sum, if n approaches infinity, also converge. In fact, Sn as n is big enough has to be bigger than or equal to, for example, a1 plus a2. This is definitely doable, right? N is big enough. Right, so that means 1 over Sn has to be bounded above. Everything is positive, right? 1 over a1 plus a2. Right. Also, we raise to the power of alpha minus 1. Right now, alpha minus 1 is positive, so still remains. Right, alpha minus 1. So that means, yes, so this part is really bounded above by some constant that has nothing to do with value of n, as n is big enough, right? So again, this part is constant. Right, so again, positive series bounded above, so it has to be convergent. And so second case, when alpha is less than or equal to 1 and also Sn diverges to positive infinity, it's going to be divergent. The reason is because in this case, I'm going to say if alpha is less than or equal to 1, my claim is that Sn to the power of alpha, right? Remember, alpha is some number that's less than 1 or equal to 1. So this looks like it's going to be less than or equal to Sn, I believe. Right? Because if you think about, also, Sn diverges to positive infinity. So when n is large enough, for example, when n is large enough, obviously we have Sn must be bigger than or equal to 0, right? That's obvious. So we have a base that's at least 1, right? And also imagine we have the power, right? Here we have the power of 1. There we have the power that's less than 1 or equal to 1. So in that case, I think, yes. For example, 2 to the power of, for example, 1/3. Obviously less than 2 to the power of 1, right? So if alpha is 0, right? See 0, then the 1 is less than or equal to 2 to the power of 0 is less than or equal to 2. Of course, true. If alpha is negative, right? So imagine 2 to the power of negative 2. That's 1 over 4. Of course, obviously less than 2, right? So this is obvious, right? So if that's the case, then let's look at an over Sn to the alpha. must be switch the direction, right? Let's larger than or equal to an over Sn, right? So when n is large enough, right? Because before the capital N, I have at most finitely many terms. And we all know that finitely many terms does not impact the convergence of a series. So all I care about is the terms that after this N, right? Okay, so let's look at let's look at, I want to start from, for example, Sn plus 1, right? An plus 1 plus all the way up to, let's say, S capital N 1, right? A capital N 1. Capital N is still fixed. Capital N 1 is large enough, right? In this case, I want to make it a little bit smaller, right? So that means I need to make the bottom a little bit bigger, right? I want to replace every denominator with Sn1, right? Because out of this many denominators, which one is biggest? Sn1, obviously, right? So Sn1 and A. So let me get sigma An. N goes from capital N plus 1 all the way up to capital N1, right? So that is equal to S capital N1 can be broken apart into two parts, right? First part is N goes from 1 up to capital N1 minus 1, right? An. Second part is N goes from No, I want to break it into from 1 up to capital N. Then I'm going to start from capital N plus 1 until capital N1. An, right? And so N goes from capital N plus 1 up to capital N1. An. So the overall thinking is very clear. It's just the notation is just a little bit messy. But here, so this part and this part are the same, right? And notice this part is only partial sum, right? Capital N is fixed. Now we divide everything by this part. That is equal to 1 plus 1. This part becomes the top. I have N goes from 1 up to capital N over sigma. N goes from capital N plus 1 up to capital N1 An. Now, in this case, I claim that as long as capital N1 is big enough, we can make sure that this partial sum is going to be bigger than this partial sum, right? Because remember, this partial sum is also fixed, right? Capital N is fixed. No matter, capital N may be very big, but doesn't matter. It's still fixed, right? So remember, Sn given to be converted, given to be divergent to positive infinity, right? So that gives us the advantage of making capital N1 very, very big, big enough so that this partial sum bigger than this partial sum, right? This is definitely achievable, right? So capital, so let's say, right, big enough. So this part is bigger than this part. So meaning this part, if replaced with that part, the bottom will become smaller. So the whole fraction will become bigger, right? So the whole bottom will become bigger. So this whole fraction will become smaller, right? So 1 plus 1, 1 over 2. If both n is bigger than capital N and we choose capital N1 big enough, right? Obviously, capital N1 is bigger than capital N, right? Both big enough, and we can, for example, continue this process over and over again. For example, I can say that if I start from, again, like I said, the subscript is a little bit messy. So if I repeat this process for k many times, if I start from, let's say, capital N sub k minus 1, then plus 1, I have A, the same thing, capital N sub k minus 1 plus 1, right? So this k just means I repeat this process for k times, right? Plus all the way up to A sub capital N sub k, right? Like I said, here is capital N plus N sub, right? Here's sub 1, sub 2, sub 3, sub 4, sub k, right? That's what I mean. So S capital N sub k minus 1 plus 1, right? Obviously, greater than or equal to, again, same process. Replace every denominator with this biggest one, right? S capital N k minus 1 plus 1 sigma n goes from n k minus 1 plus 1 all the way up to n k, right? So again, two parts. So let me just rewrite this sum into two parts of sums. So like I said, maybe we can break it apart into first part. N goes from 1 up to this subscript, right? Then goes from this subscript all the way up to this subscript. So this is what I mean. First of all, N goes from 1 all the way up to, because here I start from this subscript, right? That means I only need to subtract 1 from it. So capital N sub k minus 1, right? So again, just the abbreviation. The second sum is N should go from, from this subscript, right? Capital N k minus 1 plus 1 up to capital N sub k, right? So that this sum is the same as this sum. And this sum, again, is fixed, right? Like I said, I choose capital N1 to be big enough. So on and so forth. Capital 2 to be big enough. Capital N3 to be big enough. So it's capital N k minus 1 to be big enough. But still this is fixed. So still a fixed partial sum, right? So again, divide everything by this partial sum. Right? So this will become just 1. This will become just 1. So this will be divided by partial sum. N goes from capital N sub k minus 1 plus 1 all the way up to capital N sub k, right? So it's 1 on the top and plus 1 here, right? So perhaps plus 1. So all I need to have a look at is this one, right? Same reason. Like I said, the top sum, partial sum, is fixed, even though capital N k minus 1 is big enough, but still fixed. Now, the bottom, I say, the bottom can be big enough, bigger than the top, as long as capital N sub k is big enough, right? This is big enough. Right, this is definitely doable. Right, like I said, the whole reason is because Sn is given to be approaching positive infinity. Right? So like I said, even though this partial sum may be very big, but as long as capital Nk is big enough, this can definitely be even bigger than this sum. Right? So that means this, if replaced with that, then the top will become smaller, or the bottom will become smaller. So this fraction will become bigger. So this whole denominator will become bigger. So the whole fraction will become smaller again. So this bigger than or equal to 1 plus 1, 1 over 2. Right? So again, we've done it like repetitively, k times. Each time bigger than or equal to half, bigger than or equal to half, bigger than or equal to half. How many times? K times, right? So in the end, I say the sum. I didn't start from 1. Remember, I started from fixed n, right? N plus 1. But still fixed. Right? Until capital N sub k. Right? This is big enough. So, like I said, before capital N plus 1, there may be many terms, but still finitely many terms. So, finitely many terms does not impact the convergence of a series, right? So this part is all I need. This part is proven to be bigger than or equal to k many times of half. Right, so k over 2. Right now, capital Nk is still fixed. Right, k is still fixed. Right, n plus 1 is also fixed. Right now, I let k approach infinity. This is perfectly legal. So as k approaches infinity, right, k is big enough, right? So that means automatically capital N sub k, of course, approaches infinity. Because capital N sub k always goes faster than k, right? This is obvious, right? Capital N1, of course, goes faster than 1, right? And capital N sub 2, of course, bigger than 2, right? Capital Nk, of course, bigger than k, right? Of course, approaches positive infinity.